Okay, students, this is actually a summary of the topics of lesson 19.1 all bundled together. We started off by giving you this new function f of x equals ax squared, where we no longer have a linear equation, we have our first nonlinear equation. The question is, okay, so what happens when we start messing around with that a being the coefficient of the variable x squared? So we have four different scenarios we have to consider. What happens when a is bigger than 1? What happens when a is between 0 and 1? In other words, all types of proper fractions. What happens when a is smaller than 0? And I hope you understand what that means. That means all negative numbers. And why can a not be equal to 0? So let's start off with the first one. What happens when a is bigger than 1? In order to understand this, we have to go to decimals, and let's go ahead and just plug in x squared, and we get our characteristic parabola. Now I'm going to drag this down a little bit so it's a little bit easier to see. But notice what happens when I do let's go 5 times x squared. In other words, a is equal to 5. Now, my line is blue. Notice what happened to the red line. Kind of got a little bit more narrower. It's kind of like it's stretching. It's a vertical stretch. It's getting closer and closer to that y-axis. What do you think is going to happen if I do, I don't know, let's go with 50x squared. There you go. Look, it's even getting closer and closer and closer together. Again, it's like the two lines are being pushed this way so that it gets closer and closer. Now, I don't know if you're going to be able to see this or not, but good scenario. Let's do 100x squared. And if you look at it, it's even a little bit tighter. Again, that's what we refer to as a vertical stretch. Kind of like when you wake up in the morning and the first thing you want to do is kind of stretch your arms out and give a good yawn. That would be a vertical stretch. All right, all these have the same thing in common, and I don't know if you picked up on it, because we're not adding or subtracting anything to it. Adding or subtracting, kind of like if it was a slope-intercept form, y equals mx plus b, there's no b. So you'll notice that all of them have the same thing in common right here. They're all connected together at the axis of symmetry located at the origin 0, 0. That's very important. Now, we cannot call it the y-intercept with the letter b because it is no longer a linear equation, so we refer to that as the letter k. The letter k being replacing the letter b. So now we could come back here and say, well, what happens when a is bigger than 0? We end up with a vertical stretch. So, in other words, instead of looking like this, it looks like this. Oops. Okay. And all you're doing is stretching it vertically. Now, like we said a few minutes ago, we noticed something interesting about this. And the interesting thing is now I could put in a letter K here instead of a letter B. And now we're getting something more interesting that's happening, and we'll talk about this more later. Okay, so what do you think is going to happen if I put in a fraction? Well, fractions that are proper will do the opposite of what you just saw right here. So let's go back to decimal. Let's clear these out. And now watch this. Again, the red line is the parent graph being nothing is added, subtracted, multiplied, or divided to the function x squared. So this time we're going to do 1/2 of an x squared. And notice what happened. It's no longer stretching together closer. Now it's pulling apart. Okay, it looks like it's pushing away from each other. So let's make the fraction a little bit more interesting. Let's go with 5/7 x and squared. Again, you'll notice it's pulling apart a little bit more. Of course, that color right there isn't very helpful, so let me see if I can change my color. Okay, let's go over here. Let's touch this guy for a few seconds. And let's change it to, I don't know, blue. Okay, there we go. Again, red is the parent graph. Blue is a little bit further. The 1/2, which is black, is a little bit further. Now let's go for something even more interesting. 1/50 of an x squared. And look how flat that's getting. Again, that's a color. That's the same color. Let's see if I can change its color to something a little bit more interesting. Let's go with green. We don't have green on here yet. Now, you can see what's happening. As the fraction numerator, as the denominator is getting larger, you'll see that it's getting more flatter. We call this a vertical compression. It's being compressed. If you were to take a spring and compress the spring, you're flattening it out. So vertical stretch is when the two lines, the two axes get closer and closer together. Vertical compression, when you're a proper fraction, the lines get further and further apart from each other. Okay, and just one more giggles and grins. Let's go to 1/100 of an x squared, and you'll notice it's still not touching that value right there, which is your horizontal axis. All right, now, so we're going to go back and say what happens when you have a proper fraction as a value of your coefficient. You have a actually, let's make this in red so it's highlighted. You have a vertical compression. Okay, now, what do you think is going to happen if we make it negative? If we were to make it negative, let's get rid of all these guys except, of course, for the parent graph. Now, I don't want x squared positive. I want x squared negative. And let's bring it up so you can see it. And look what it did. We refer to that as a reflection. It reflected across the x-axis. So instead of it going up, actually I said x-axis, that's the y-axis. Instead of it going up, it's going down. So that's the only thing that's different. Everything else is exactly the same. So if I had a vertical compression, 1/2 x squared, and the only thing I wanted to do is make it negative. Look, it's the exact same dimensions. It's just flipped across the y-axis to the other side. What if I wanted a vertical stretch? Say, for instance, I wanted to go to 20x. Again, 20x, you notice it's the black one, and the black one is kind of squeezed a little bit tighter than the red line. And if I just change it negative, the only thing that happens is it reflects across the y-axis. Same type of graph, same look, just reflected. All right. So here we go. So we're going to call this one a reflection. Actually, I probably just spelled that wrong because that's muscles. I don't want muscles. I want visual. Okay, so it's a reflection across the y-axis. All right, this last one, cannot be good. All right, so why can this not be good? Because what happens if a is equal to 0? What's 0 times anything? Yep, you're right, 0. So if I plug in this 0 right here, I no longer have a function. I just have f of x equals a constant 0. Therefore, that makes no sense at all. So we can't have it. Can't work out that way. So I hope this clarifies a few topics. If you have any questions, shoot me an email. Have a good day.